Hello again, and welcome to another review session for your final examination in Calculus 3208. This is brought to you, of course, by CDLI as always. And today we're going to take a look at our first section under the very large umbrella of applications of derivatives. And the first thing we're going to look at is something called rectilinear motion. This is not a specific outcome in the course as such, but these kinds of problems can really be asked even without that being the case, because they are actually very, very common applications of derivatives, and probably even how in many of your classes the way that derivatives were introduced as a rate of change. So let's get down to business. So rectilinear motion, or sometimes just called linear motion for short, we're going to review the concepts of motion and rates of change, and we're going to solve some problems involving this stuff. So not a whole lot going on there, but we'll roll right along. So basically we've got to talk about what this means. So when we talk about this special kind of motion, we often call it motion along an axis. So for motion to be motion along an axis, all that really means is that it's motion that can only go basically along a straight line. So you can go in one direction or the other, forward or backward or left or right or up or down, but it has to be exactly a straight line. So what we're going to do for our purposes to keep it simple is we're going to think of our straight line that we're following as being an x-axis. So we're going to talk about motion along an x-axis, which is usually the standard way to do it, although sometimes you'll see forward, back, or up and down. And we're going to talk about some conventions first of all. So because we're moving on an x-axis, we'll talk about our position at any given time as being an x-coordinate. So we can say x is a function of time t. So as time passes, the value of our x-coordinate can change as we move. So if we're at the origin, then x of t would obviously be equal to 0. And at any time, if we're to the right side of the origin, then what that means is that x is going to be a positive coordinate. And if we're to the left of the origin, x is going to have to be a negative coordinate. So those are the basics of what this position stuff is going to be. So in come now the rate of change question that has to deal with this stuff. So we often consider the rate of change of our position, or the derivative of position, as a function of time with respect to time, is what we call the velocity. So velocity tells us how fast our position is changing. So if we look at the way the conventions are here, we say that if the velocity at time 0, or the derivative of position at times, or at any time t, is equal to 0, we say that whatever object, or sometimes we just call them particles in these cases, whatever object it is actually going to be stopped. So if your velocity is 0, you're not moving. If your velocity is a positive value, that means you're moving to the right. And if your velocity is negative, it means you're moving to the left. So it's possible to have a positive x-coordinate and a negative velocity. It just means that you're positioned to the right of the origin, but you're moving back toward it, so you're moving toward the left. So those things don't have to be consistent like that. And that's part of what makes this stuff a little bit fun here. So the last thing we're going to talk about is the acceleration function. And the acceleration function is basically the second derivative. So it's the rate of change of the rate of change. So it's the second derivative of your position, which will be the first derivative of your velocity, or how fast your velocity is changing, and that will be your acceleration. Now, many of you have probably taken physics classes in high school, and one thing that's sort of limited about your acceleration issues in physics, especially in your kinematics units that you study, is that invariably you deal with constant acceleration situation. So you do have accelerated motion, but that acceleration is always a constant. Now that we understand some calculus, we don't have to live by that restriction anymore. And certainly if you study physics in university, you won't have to live by that restriction either, because it will become calculus based now. So one thing we're going to do is just look at the sign conventions for acceleration. The first one is that if your acceleration value is 0 at any given time, it means not that you're stopped, you can still be moving, it just means that your velocity is not changing because we have no change in it. So basically it means you're moving at a constant speed. Or you could be stopped, but most likely you're just moving, but at a constant speed. If your acceleration is a positive number, that means you're accelerating to the right. So basically, sometimes we just think about acceleration as the result of a force. So if you're accelerating to the right, then that means there's a force that's pushing you in that direction. That doesn't necessarily even mean that you're moving in that direction. You can be moving to the left but being accelerated to the right at the same time. And similarly, we can have, if our acceleration is negative, we're going to be accelerating to the left. And we have to sort of look at that sort of in detail. How can I be moving in one direction and accelerated in the other at the same time? Well, that's all going to depend on whether you're speeding up or slowing down. So let's take a look at this now. Speeding up or slowing down, there's 4 different cases. So these are the conventions that we use in calculus when we talk about motion. If both your speed, or your velocity I should say, and your acceleration are positive, that means that you're moving to the right and you're being accelerated to the right at the same time. So you're accelerating in the direction that you are moving, so you will be speeding up. And if we jump all the way down to the bottom right here, it would be the same thing. If our velocity is negative, that means that we're moving to the left. And if our acceleration is also negative, we're being accelerated leftward, so we would be speeding up. So it seems kind of strange to think of a negative acceleration as meaning that you're speeding up, but the key is those signs have to match. So if both are positive or both are negative, then you're going to be speeding up. And if we look at the second case up on the top row here, we see it says that the velocity is positive and acceleration is negative. So that would mean that you're moving to the right, but you're being accelerated to the left. And if that's the case, then even though you are moving to the right, you're slowing down. And eventually, if that continues, you will stop. And in the last case that we're going to see down here, if you're moving to the left because your velocity is negative, and your acceleration is positive, accelerating you to the right at the same time, then we have a conflict in those things, and that's going to slow down your motion. So that's when you're slowing down. Okay, so those are important things. We often think that if acceleration is negative, we're slowing down, and if it's positive, we're speeding up. But that also depends on the direction in which you're moving, so we have to be careful about that. All right, example 1. It says a particle moves along an x-axis so that its position at time t is given by this equation, which is a polynomial, it looks like. It says find equations for velocity and acceleration. So as we saw, those will just be the derivatives here. So the velocity at time t, we know should be the derivative of our position function at time t. So based on that polynomial, I'm going to use the power rule for each term, giving me 3t squared minus 12t plus 9 as long as time is positive, which I've never heard of time being negative. It doesn't make much sense in the context of our physics business or our calculus business that we're dealing with here. So there's our velocity at time. So to get acceleration at time t, we know that that's the rate of change of your velocity. And the rate of change of our velocity is the second derivative of our position function. So using power rule again, I'll have 6t minus 12. So not much to that. We've got acceleration is just a linear function, 6t minus 12. So then we have to answer another question that says, when is the particle stationary? So stationary means stopped or not moving. So we have 3 different functions, and the idea is to decide which one to use and how to use it. Well, if the particle is stationary, what we said earlier is that means that you are stopped and your speed would actually, or your velocity even, would actually be equal to 0. So that for the particle to be stationary here, this function, our velocity function, has to be equal to 0. So we just simply solve this equation to find out at what time or times we're going to have that being the case. So I have to solve a quadratic. Everything's divisible by 3, so this simplifies quickly. And it looks like this is going to factor nicely. So we have t minus 3 by t minus 1. And so if that's the case, at time equals 1 second or 3 seconds, assuming that this is given in time and seconds and position in meters like we use for standard units in physics, then those are the times at which our particle will be stationary. Okay? Alrighty, let's try another one. For the same situation as in example 1, so the same situation and all of those equations that we just derived are all rewritten here. We're asked to decide when is the particle moving leftward. Okay, so this is a little more interesting now. What we saw is that the particle was stopped at times t equals 1 and 3. So to say when our particle is moving leftward, we want to find out, remember, when is our velocity function going to be a negative value. So in order to get that, what we have to do, the easiest thing to do, is just do a number line that looks like the same kind of thing we would do if we're looking to decide whether a function is increasing or decreasing on a graph. So what I'm going to do here is I'm going to draw a number line, and actually I'm going to adjust it a little bit. I'm going to fix this side and say we're going to get rid of that arrow that we had over there, and we're going to say the number line has to start at 0, but time can't be negative, so nothing before that. And then I'm just going to make a little mark for time equals 1 second, and then sometime later over here for time equals 3 seconds. And I'm going to look at those two spots as being places where I'm stopped. And then what I have to figure out is, when is my speed or my velocity going to be equal to 0? Sorry, when is it going to be less than 0? So I'm just going to take my velocity function, and I'm going to test values of it in each of the 3 intervals that this divides us into. So the first interval goes from 0 to 1, then from 1 to 3, and then from 3 onward. So if I take, how about a number like 2? That's a good one to start with. That'll test this interval in here. So let's have a look at what that does to our speed, and then that'll tell us what that does to our position. So if I let t equal 2, then my velocity at time 2 would be equal to 3 times 4 minus 12 times 2 plus 9. So let's see, that's 12 minus 24 plus 9, giving us a value of -3. So at that point right in here, our velocity function is negative, which means that our position function tells us we're moving leftward. Okay, so let's test a couple of other points. How about at time equals 0.5? So velocity at 0.5 will give us 3 times 0.5 squared, which is 0.25, minus 12 times 0.5, and then plus 9. So we can put all that stuff together. So 3 times 0.25 is just going to be 3/4, or 0.75. And then we've got to subtract a 6 and add 9. And what we can quickly see there is that gives us a positive answer. So out here our velocity is positive, which means we'd be moving to the right. And then we've also got to check, oh sorry, that was out here, wasn't it? Positive, and we're moving to the right. Excuse me. So we'll leave those there. We might not have to fix them. We'll see what the answers come up to be now. But we can see that that was at 0.5, and another test point, let's say we go for 4. So our speed at time 4 is going to be 3 times 4 squared minus 12 by 4 plus 9. So this gives us 3 times 16, so that's 48, minus 4 times 12 is 48, and plus 9, that gives us another positive number. So we were okay to leave it. It was fine anyway. All right, so the question says, when is the particle moving leftward? And it's only between times 1 second and 3 seconds. So we could say when time belongs to an interval that starts just to the right of 1 second and goes just to the left of 3 seconds. And that would be our correct answer there. All right, so before I get on to part B here, what I'm going to do is just clean up this slide a little bit. Take some of this stuff out of here so we have a little more space. All righty. Now, the next thing we have to look at is, when is this particle's speed increasing? So when is it speeding up? So not velocity increasing, but when is its speed increasing? So it'll be speeding up, or it'll have an increasing speed, remember, whenever the sign of the acceleration and of the velocity are the same. So if they're both negative or both positive. So what we have to do is something similar to what we did above for velocity, only now we have to do it for our acceleration. I should really use proper straight line to do that. So just let me get rid of that one. All right, so let's use a proper line then. Okay, so I have to now draw another number line. And on this number line, I have to look for places, first of all, where my acceleration would be 0. So acceleration was 6t minus 12. So I'm going to let that equal 0 and solve for t. And very quickly we come up with an answer of t equals 2. So 0 is sort of the starting position here. And so we can put all the times in the world we want on here, but the only one we're really interested in is at time equals 2. And so we're just going to test either side of that using our acceleration function to decide what that means for our velocity function. Okay, so if we test a point at 1, let's say, my acceleration at time 1 is going to be 6 minus 12, which is negative 12. So over here we're negative, which means our velocity is going to be we're accelerating to the left rather, And if we take at time equals 3, acceleration at 3 now, we're going to have 18 minus 12, which is positive, which means we'd be accelerating to the right. So now if we compare the two little sign diagrams we have, the one up top and the one down the bottom, we're looking for places where we're both positive or both negative. So my acceleration is negative from 0 up to 2, and then it's positive everywhere after that. So from 0 up to 2, the only place that I'm going to be negative for my velocity is from this point 1 here up to 2 there. That's going to be negative. So we're going to be increasing speed on that first interval. We can say from 1 up to 2. We're increasing speed and we're moving leftward. Okay. So is there any other place where we're also going to be increasing speed besides this interval? Well, let's see. We're positive everywhere after 2, and our original velocity graph that we drew up here is positive everywhere after 3. So they're going to have the same sign from 3 on to infinity. So we put those two together and we can see that we're speeding up or increasing our speed between time 1 and 2 and between times 3 and on forever. Okay, so there's a lot of detail on that one. So here's one more. It says a particle moves along an x-axis with that position equation. So we have to do two things. Find the velocity and acceleration functions, so just taking some derivatives, and then show that the particle is always moving to the right. So let's get those derivatives out of the way first. So velocity is going to be the first derivative here. So that'll be 1/2, if I think of this as an exponent, of b and c. We're going to assume are simply just constants here. We're saying that x is a function of time as a variable. So that's going to be times t squared to the power minus 1/2. And then we're going to multiply that by the derivative of the stuff inside using chain rule here. And that's going to be 2 times c squared times t. Okay, so if we simplify our velocity equation relatively quickly, the 2 and 1/2 can cancel, and I'll have a numerator of c squared t, and in the denominator I'll have the square root of b squared plus c squared t squared. Okay, so there's my velocity function after I differentiate my position function. So the next thing I have to do is take the derivative of that guy so that I can get my acceleration function. So this one looks like a quotient rule might serve us best. So my acceleration as a function of time then. The derivative of my numerator, c squared is constants, so that times t will have a derivative just of c squared, multiplied by denominator, which is this stuff, b squared plus c squared t squared, minus the derivative of my denominator. My denominator is actually, if you look carefully here, the denominator is exactly the same thing as our very original function that we started with, isn't it? So if I write the entire velocity function, I know that that's the derivative of that. So this business right here, c squared t over the square root of b squared and c squared t squared is actually the derivative of just the denominator, and then I have to multiply that again by the numerator, which was c squared t again. And all of that gets divided by the denominator squared, and so my denominator squared will just be b squared plus c squared t squared, and the square root squared cancels out. So there's an acceleration function, which we could simplify, but we weren't asked to here, so we're going to leave that in unsimplified form. Not a big deal, just practice with quotient rules, basically all that is. And it says now that we have to show that the particle is always moving to the right for part B. So if the particle is always moving to the right, that would mean that the velocity function always has to be positive. Well, let's take a look at what we got for our velocity function. It was c squared t divided by the square root of b squared plus c squared t squared. Okay, so let's see if we can just discuss this first of all. If we look on the numerator, c squared times t, well, it doesn't matter whether c is a positive or negative constant. Once I square it, it becomes positive. So the numerator is going to have a positive factor here, multiplied by t, and we're told right in the description of the problem that t is never going to be a negative function. It could be 0, but that's only at the very beginning. So after that time, it's not an issue. So we could have a 0 up there, but we're going to assume it's positive for everywhere except for the very starting time. And then in the denominator, I have to take the square root of b squared plus c squared times t squared. And all of these things are squared, so they're all going to be positive. And of course, this is a principal square root, so it's only a positive square root, no negative there. So that means I've got all positive stuff over all positive stuff, which means that my velocity function is indeed always going to be a positive, and therefore we're always moving to the right. So not a whole lot to that. Okay. So here's the or-turn question, very similar to some of the stuff that we just did. So if you want to pause the video and work it out, go for it. I'm going to flip to the solution now. So here is the solution to the or-turn question, all worked out in the required details. And I'm just going to summarize now all the things that we talked about in this section. So we said for rectilinear motion or motion along a line, acceleration is the derivative of velocity, and velocity is the derivative of position. Or if you want it, you could say that acceleration is the second derivative of your position function. So to relate velocity to speed, we talk about a particle speeding up or slowing down when its velocity and acceleration have the same sign, and opposite signs means, they're slowing down. Same sign means they're speeding up. And we use sign graphs to determine the directions of motion and of the direction of acceleration. Okay? So I hope that's helpful. Just a little bit of an application there. You might not see that ever on an exam, but you never know, you might come across it. So we took a look at it anyway. Happy studying.